Long before power plants, electrical grids, and towering transmission lines, the world lived by one simple rule. The sun decided when the day ended. As daylight disappeared, nearly everything came to a stop. There were no electric lights, no powered machines, and no cities glowing through the night. For thousands of years, the only reliable sources of power came directly from nature. But these machines only worked where nature allowed them to. Everything changed when engineers learned to harness the power of steam. Heat was no longer just warmth. It had become mechanical motion. Steam engines powered factories, locomotives, and ships, transforming entire industries. But steam power had one major limitation. It could only deliver energy where the machine was built. Scientists soon discovered something extraordinary. Motion itself could create electricity. This simple principle became the foundation of every modern power station. Unlike mechanical power, electricity could travel far from where it was generated. Soon, enormous power stations began supplying electricity to entire cities. Electricity quietly became the invisible foundation of modern civilization. As civilization expanded, the demand for electricity grew faster than ever before. Coal-fired power stations supplied much of this growing demand. Engineers began searching for a source of heat that contained far more energy than burning fuel. Inside every atom lay an astonishing amount of stored energy. Instead of burning mountains of fuel, engineers learned to unlock energy from atomic nuclei. Humanity's search for power had reached one of its greatest engineering achievements, the nuclear power plant. But how can something smaller than a fingertip power an entire city? To answer that question, we must travel into the heart of a single uranium atom. Imagine standing only a few hundred meters away from one of the most powerful machines ever built. From the outside, it seems almost peaceful. Yet, hidden behind those thick concrete walls, enough energy is being produced every second to power an entire city. If a nuclear power plant generates so much energy, why does it appear so quiet? Where are the giant furnaces? Where are the burning mountains of coal? How can something smaller than an atom power millions of homes? For many people, the word nuclear immediately brings dramatic images to mind. Movies often portray nuclear technology as mysterious and terrifying, but those images tell only a tiny part of the story. Every day, hundreds of reactors quietly generate electricity around the world. The surprising truth is that a nuclear power plant is essentially one of the world's largest steam engines. Everything inside the plant is designed around one goal: producing steam. Instead of burning fuel, the heat comes from deep inside the nucleus of an atom. Each tiny fuel pellet contains an astonishing amount of energy. Thousands of these pellets are stacked inside long fuel rods. Every valve, pump, sensor, and safety system works together to keep the reaction perfectly controlled. Billions of atoms split every second, producing enough heat to power entire cities. Now it's time to travel deep inside the reactor and follow the incredible journey of energy from a single uranium atom all the way to your home. Everything begins with something so small that it cannot even be seen. Hidden inside that tiny nucleus is an extraordinary amount of stored energy. Every atom consists of electrons, protons, and neutrons. Although the nucleus is incredibly small, it contains almost all of the atom's mass. Natural uranium contains mostly uranium-238, while only a tiny amount is uranium-235. Uranium-235 has a remarkable property. It can split when struck by a slow neutron. For an instant, the nucleus becomes unstable. Then, it suddenly splits apart. This process is called nuclear fission. The split releases heat, radiation, and additional neutrons. By itself, one fission event releases only a tiny amount of energy. But inside the reactor, billions of these events occur every second. The released neutrons strike nearby uranium atoms. Each new fission releases even more neutrons. This continuing sequence is called a chain reaction. Inside a reactor, the chain reaction is carefully controlled. Every reaction is designed to produce only one more reaction. That perfect balance allows the reactor to operate continuously for months. The heat produced is extraordinary, but it must be removed continuously. In the next chapter, we'll step inside the reactor vessel and discover how flowing water carries this incredible heat safely away from the fuel. Deep inside the containment building sits the heart of the entire power plant, the reactor vessel. From the outside, it looks like a giant steel cylinder. Hidden inside is where the journey from atomic energy to electricity truly begins. Hundreds of fuel assemblies stand in perfect rows beneath the water. Everything appears calm, yet billions of atoms are splitting every second. Each fuel assembly is built from dozens of long fuel rods. Inside every fuel rod are thousands of uranium fuel pellets. Each tiny pellet stores an astonishing amount of energy. Hundreds of fuel assemblies are arranged in a carefully calculated pattern. Heat begins moving outward from the fuel pellets. The fuel never burns, it simply becomes hotter as fission continues. Massive pumps circulate purified water through the reactor without interruption. The water cools the fuel while carrying away enormous amounts of heat. The same water also helps slow neutrons inside the reactor. Despite reaching temperatures above 300 degrees Celsius, the water never boils. Enormous pressure keeps the water in its liquid state. The superheated water now leaves the reactor carrying an immense amount of thermal energy. Hidden among the fuel assemblies are the control rods. By raising or lowering the control rods, engineers precisely control the chain reaction. Now the reactor has produced heat, but heat alone cannot power a city. In the next chapter, we'll discover how giant steam generators transfer that heat into pure steam capable of driving turbines weighing hundreds of tons. As the superheated water leaves the reactor vessel, it carries an enormous amount of thermal energy. Despite its extreme temperature, the water never boils because of the immense pressure inside the primary loop. The coolant now enters one of the largest heat exchangers in the plant, the steam generator. Inside are thousands of narrow metal tubes carrying the hot reactor coolant. Around those tubes flows an entirely separate body of water. The two water systems never mix. Only heat passes from one system to the other. As the secondary water absorbs heat, it begins to boil. Liquid water transforms into high-pressure steam. The steam now stores enormous amounts of energy. Before leaving, the steam must be dried. Even tiny droplets could damage the turbine over time. Only clean, dry steam continues toward the turbine hull. These pipelines are so large, a person could stand inside them. Meanwhile, the primary coolant begins its return journey. Powerful pumps keep the coolant circulating continuously. Two separate water systems now work together without ever touching. The steam has finally reached the machine it was created for. In the next chapter, we'll enter the turbine hall, where this invisible flow of vapor will spin a machine large enough to power an entire city. High-pressure steam races through enormous insulated pipes toward the turbine hall. The turbine hall houses one of the largest rotating machines ever built. Steam enters carefully designed nozzles that convert pressure into velocity. The accelerated steam strikes the first row of turbine blades. Each blade captures a small amount of energy. Thousands of blades work together to produce an enormous turning force. The giant steel shaft accelerates toward its operating speed. The turbine blades move at astonishing speeds. Steam expands as it passes through multiple turbine stages. The final turbine stages are enormous. The rotating shaft is directly connected to the electrical generator. Inside the generator, a massive electromagnet spins within copper coils. The changing magnetic field generates electricity. Mechanical energy has now become electrical energy. A single reactor can power hundreds of thousands or even millions of homes. Before leaving the plant, the electricity enters giant transformers. High voltage power lines carry electricity across vast distances. Within moments, that electricity powers homes and industries. But the steam still has one final journey to complete. In the next chapter, we'll uncover one of the most misunderstood parts of a nuclear power plant: why the giant cooling towers release clouds that look like smoke, even though they're producing nothing more than water vapor. By the time steam leaves the final turbine, it has given up most of its energy. Before the cycle can begin again, the steam must become water. Inside the condenser are thousands of cooling tubes. The cooling water and steam never mix. The steam begins condensing into liquid water. The vapor rapidly collapses into liquid. This creates a partial vacuum inside the condenser. The vacuum improves the efficiency of the turbine. The condensed water collects beneath the condenser. Feed water pumps send the water back through the system. Meanwhile, the condenser has absorbed an enormous amount of heat. The warm cooling water now travels toward the cooling towers. Cooling towers are among the most recognizable structures in the plant. Many people mistake the white cloud for smoke. Inside the cooling tower, warm water is cooled by natural airflow. A small amount of water evaporates, removing heat from the rest. The white cloud forms when water vapor condenses in cool air. The cooled water returns to the condenser. Three separate water systems now work together in perfect harmony. The engineering is extraordinary, but perhaps even more remarkable are the layers of safety that make it possible. For more than 70 years, nuclear power has supplied electricity to millions of homes around the world. But the story of nuclear energy is far from over. In many ways, it is only just beginning. Every year, the world's demand for electricity continues to grow as cities expand, industries evolve, and billions of devices become connected. Future power plants must produce more electricity, operate more efficiently, and deliver reliable energy around the clock. Engineers are already designing a new generation of nuclear reactors, smarter, simpler, and even more efficient than today's designs. One of the most promising ideas is the Small Modular Reactor, often called an SMR. Instead of constructing one enormous reactor, engineers build compact reactor modules that can be manufactured in factories and assembled on site. Factory-built modules could reduce construction time, lower costs, and make nuclear energy available in regions where traditional reactors would be impractical. Beyond today's technology, scientists are developing Generation 4 reactors designed to improve fuel efficiency, reduce waste, and operate at even higher temperatures. Some advanced concepts replace solid fuel rods with molten salt carrying dissolved nuclear fuel. Instead of water cooling the reactor, liquid salt transports heat at extremely high temperatures. Other designs operate at temperatures far beyond conventional reactors, opening the possibility of producing industrial heat and clean hydrogen in addition to electricity. Researchers are also exploring ways to extract more energy from nuclear fuel while reducing long-term waste through advanced fuel cycles. Many future reactors are designed to rely even more on the laws of physics themselves. Gravity, natural circulation, and convection can remove heat without pumps or external power. Artificial intelligence is beginning to assist engineers by analyzing enormous amounts of operational data, detecting subtle patterns, and supporting predictive maintenance. Autonomous robotic systems are already inspecting reactor components in environments that are difficult or hazardous to access. Beyond nuclear fission lies an even greater challenge: nuclear fusion, the same process that powers the sun. Instead of splitting heavy atoms apart, fusion combines light atoms together, releasing extraordinary amounts of energy with no chain reaction. Creating and controlling temperatures hotter than the center of the sun remains one of humanity's greatest engineering challenges. The future of electricity will likely combine many technologies working together. Nuclear reactors, renewable energy, large-scale storage, and intelligent electrical grids may form one integrated system. Whatever technologies emerge, one goal remains unchanged: to provide reliable electricity for a growing world while continually improving efficiency, safety, and sustainability. Humanity's search for power has carried us from flowing rivers and steam engines to splitting atoms and exploring the possibility of fusion. Every generation has expanded the limits of what engineering can achieve.